Hi, this script is for the material testing. We have studied 4 chapters already, and this script is going to do the first part of the chapter 5. It's going to talking about the characteristic of tests. And in our course, we have many type of tests that can be tension tests, compression tests, shear tests, fractional tests, and fatigue tests. And the learning objective of this course is to let you understand the characteristic of these tests. You may start by the first one, static tension. As you may know, in the Thailand Industrial Standard, or the TAS, we have specification that specify the mechanical property of the given material. For example, the structural steel, the TAS 116 indicated that the yielding stress of the Fe24 steel should have the yielding stress at least 2,400 kg per square centimeter. And also, it specs that the ultimate stress must be at least 4,100 kg per square centimeter. The percent elongation, these two indicate the elasticity or plasticity also of the material. The Fe24 must have at least 23%. And also the stiffness indicated by the modulus of elasticity of 200,000 kg per square meter or 200 gigapascal. Okay, this kind of mechanical property obtained from the tension test. So we do the tension test, we plot the stress strain diagram curve, and then we determine the given, the specified mechanical property as I mentioned before. Okay, this is the example of structural steel section. It may have Fe24 or Fe30, and then as I mentioned, the Fe24, you got to have yielding stress at least more than this, ultimate stress at least more than this. This indicate the strength, and this indicate the ductility of the material, and this also indicate the stiffness. If you test a steel and it won't pass one of these, that means the steel won't pass the TAS 116. That means you get to reject that steel back to the factory and asking them for the new set of the structural steel. Okay. What should we consider between the tension test and compression test? As you may see, we have many structure that built by the steel, and this is one of the bridge truss, that's made of steel. And you may see this bridge truss, when the train come past to the bridge, what happens is the bridge gonna deform, okay, like this. And the member of the bridge, some of them will be in compression and some of them will be in tension. Okay, and you may test the steel by the compression or by the tension test. However, testing steel in tension is more convenient than in compression. So in our lab or in Astm or TS specification, they will ask us to test the steel, okay, by the tension test. And it should be noted that the steel have the property in tension and in compression the same, especially when it is in the linear elastic range. Okay, and for the author, that's the reinforced concrete. Okay, we may construct the reinforced concrete to be the column of the structure, and then the column usually subjected to compression. That means if you do the free body diagram, the column will subjected to the force on the top and on the bottom. So the concrete is usually tested by compression because most of the concrete used to resist the compression, and also the concrete has high compressive strength, okay, compared to low tensile strength. The concrete has the tensile strength only 10% of the compressive strength. Is maybe 10 to 15% of the compressive strength. So most of the concrete we test it in compression. Okay, so the first one, we consider the application of the material in the structure, and the metal is not the steel. Usually it includes the steel and aluminum. Okay, usually support the tension in the structure since it has high tensile strength, and is usually tested in tension tests. Concrete and brick, not the concrete, is also the brick, are usually used to support the compression in the column or in the wall since they have the high compressive strength. So they are selected to test in compression. And the second, the materials such as timber. Timber is a special. Timber has a grain. Okay, the grain of the timber usually in the direction of the trunk of the tree, and when the timber used to resist in the real application, okay, most of the timber will subjected to, if this one is the applied force, okay, you may distribute the applied force into one in this direction. This is going to be 3000. This is vertical times 4 divided by 5, and another one going to be in this horizontal direction. That is going to be 3000 times 3 over 5. Okay, this force will be resisted by what? By the shear force of the wood. Okay, and this force also will resisted by this sigma of the wood. So in this application, the wood subjected to the tau, okay, that's tying to shear this portion, and is subject to the normal force. This is going to be this P over A, or it's going to be the force here divided by the area, and this one going to be the force here divided by the area. That's I'm sketching here. Okay, that's it's going to be the V over A. So most of timber, even though they has very high tensile strength parallel to the grain, the timber didn't use much in tension. Most of the timber they are using in compression, even though they have the low compressive strength and even though the low shear strength, but the application of timber usually used to support compression and shear in the structure. And that is the reason why in our study we test the timber in compression and in tension. Okay, another example is here. Okay, if you draw this in 2 dimensions, you have a piece of wood, and then it's subjected to 5 kilonewton, and the wood have the hole here, and then during the application of the 5 kilonewton, the force will apply over here of 5 kilonewton. And then if you draw the free body diagram of this part of this is going to occur what? is going to shear the wood in this direction, and then if you draw this portion of the wood, you may have that the green force gonna push, oh sorry, the green force gonna put this one, this one up, this one up, okay, and the wood gonna be in shearing force to resist this. And since this is two shear force on the left and on the right, so this is going to be what we call the double shear. Okay, and since this one is only in one plane of shear force, this is going to be, sorry, this is going to be single shear. Single shear is going to be SINGLE, single shear. Okay, there are different kind of shear. So the second one is based on the differences in mechanical property of material under various loading. Okay, the first one is about the application. Steel usually used in tension test, in tension test. Concrete usually used in compression, so it has compression test. For this one is depend on what we use. The timber, most of timber used in compression and shear, so the timber going to have the compression test and shear test. The third is about the installation of the specimen. If you consider the concrete, this is a concrete specimen, and this is for the compression test that we mentioned about it before. Okay, but in some time we also interested not only the compressive strength of the concrete, we also interested in tensile strength of the concrete. Okay, we cannot cast the concrete to be the same specimen as we test for the steel. It's really hard to cast concrete like this. It's really hard. Okay, so it's inconvenient to test the concrete for the compression by doing this. So the Astm specify the splitting tensile test, in which the concrete gonna lay horizontally and subjected to the force applied to the specimen in this direction. So what happened when this specimen subjected to the force? The force will have the arch action. Okay, have the arch action. The arch action going to move to this direction, and then it's going to produce what we call the resultant force. That's acting on this element. Okay, this element, and also this going to produce what? Going to produce, when it's going to move this way, it's going to produce the cracks along this section of this specimen. That's we call this is the split tensile test of the concrete. Okay, the third one, concrete is brittle material. Okay, it's very hard to produce the specimen of the concrete for the tension test and for the installation of the concrete. So the concrete will test by splitting tensile test. Okay, in which the concrete is subjected to compression, but the compression will produce the crack of the concrete in the tension manner. Okay, for the specimen of some metal such as the steel specimen for the tension, most of that steel will need to have big end like this. and this end. This end will put into the testing machine, the universal UTM testing machine. And what happened is they need to 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 grind the steel portion of this out. Okay, and to make this one is smaller than at the end of the specimen. So when you test this one, the specimen will fail in this area. Okay, and in this area you also measure the gate length. The gate length is going to be the L sub O. You also measure the diameter is A sub O. So when you measure the force, so you get stress equal to force divided by A sub O. And also you can determine the strain. The strain equal to elongation divided by L sub O. So we reduce the section at the middle of this specimen to force the failure to be occur in this area. And next, there are transition area between that middle part and that's the end part is going to be in this area. And you can see this is kind of a smooth curve. Okay, end of the specimen is large than the middle portion of the specimen because we like to force the failure occur at the middle. However, there are transition between the end and the middle part over here. That's to let the stress transfer smoothly between the end and the middle part. So this for smoothly transferring of the stress. Okay, and there's also type of the end. Most of the time that they have is depend on the testing machine that we use. Some may have the pin end, some may have the thread end, some may have the shadow end. We also have the thread end in our lab number 3. Okay, and when you have the specimen, you got to take a good look at the specimen. Is it have some defect or not? Because the defect specimen will provide low mechanical property. For example, the first one, the center line of the reduced section and the center line of the end are not coincide. So that is going to produce some moment due to the eccentricity of this. The second, you may see the center line this time. The center line of reduced section and the end, they are in some different angle like this. And the third, the two sides of reduced section are in symmetry. So when you catch the specimen, you may have some problem with this installation of the specimen. And also the last one, you have the hocking like this. This is going to be the weak point of the specimen and the specimen will start to fail here. This kind of defect will produce the specimen with low testing results. We should not use it. When we found one of them, you should reject that specimen. And also, in our test, as I mentioned, for the test number 3, we have the thread end like this picture. Okay, and can you tell me which one going to be the cast steel, which one going to be which one going to be the cast iron, which one going to be the structural steel? Which one? This is going to be steel. Okay, you can see it in our lab. This one going to be the cast iron. So the American Society for Testing and Metrology, or ASTM E8, okay, is specify the specimen for the steel in this portion. And for the cast iron, the specimen supposed to follow this portion. Okay, So when you go to work next, when after graduate, you may have a chance to check the appropriate specimen that we are going to use in your real work. Next, coming back to the tensions to finding the tensile strength of the concrete. Okay, and we also mentioned that we have the problem of producing the concrete specimen for the direct tension test. So Astm specify the splitting tensile test by Astm C496. The specimen is the standard cylinder specimen. However, they're going to lay like this. Laying like this, produce what? Laying like this under the compression, as I mentioned before. Okay, the stress will transfer in this direction. And what happened is, there is going to be the stress going to be move in like this, and by the third law of Newton, they are going to stress that's going to separate the beam into crack like this. Okay, the stress, one of the stress put here and another put here, they are going to have the stress that's going to push in this direction. The same thing occur here, and there is stress to produce in this direction. However, by the third law of Newton, there is going to be the tensile stress occur across the section of the cylinder, and then you can compute the tensile strength of the concrete. That is the F sub CT. F sub C is concrete, T is tension, equal to 2 times P divided by L is the length, D is the diameter. So we have the lab that you're going to use this equation for the tension test of the concrete, and you will find that the concrete is going to have the low tensile strength compared to the tension. Usually is about 10 to 15% of the compressive strength. Okay, and then you may read the reason of this cracking over here again if you won't understand what I'm saying. And this is also what is going to explain what happened in the splitting tensile test, as this stress sigma 1 over here gonna make this specimen crack in this direction. And what does the tension test we have in our lab? In our lab, we have 3 types of tension tests. One is the Poisson of the rubber. You may see we put the weight here, and we have this end fixed to the steel rod. Okay, so this one going to be in tension. For the lab number 3, we do the tension test of the steel and cast iron. In the lab, we already have this already. We put the specimen here, and when you rotate this, what happened is this one going to move up, and this one going to be fixed. Okay, so the specimen going to be in tension. And also this one for the split tensile test of lab 7. This is going to be 2000 kilonewton compression machine. Do you feel about 2000 kilonewton? Do you feel about this? 2000 kilonewton gonna be 2 million newton. 2 million newton is about 200,000 kilogram. That is about what? That is about 200 ton. Okay, in Thailand, this is about 10 wheeler. Okay, that's 20 ton. Each wheeler, when they have the loading on the wheeler, is going to take about 21 ton. That's about that. That is going to take about 10 wheeler. Okay, some important point to note when you do the tension. You got to detect the specimen. If they have the defect, you got to recheck it. Okay, testing machine is going to be a small UTM, or it's going to be the big 200 kilonewton UTM, that's a big cow bigger, or it's going to be UTM with 2000 kilonewton. Speed of the test. Speed of the test is supposed to be with the static test. Okay, we should not put too fast loading into the specimen. And you also need to notice some difference in the behavior of the material, especially when it changes from the elastic to the plastic region. That means in lab 3, we must to change from load controlling test to the displacement controlling test. I will discuss this later about the load controlling test and displacement controlling test. And you also must observe the mode of failure of the specimen, the cast iron. You know what type of failure the cast iron go to fail? The cast iron go to fail by piston failure. That's for the cast iron. For the steel, it's going to be fail in ductile failure. The steel can elongate a lot before failure. But for the cast iron, it can deform very small when it failure. And for the loading control test, there are two types of the controlling tests in our lab. And actually, the displacement controlling test is very good test that can be used to test everything. But we got to learn the loading control test to have a more depth understand of what we test the material, the metal in tension. Okay, load controlling test. What we do is we separate the load at equal intervals such as when the load of 0.5 kilonewton, the loader asks the friend lead the displacement, and then it's increased another 0.5 into 1 and asks friend to read the displacement, and increase to 1.5, ask friend to read displacement 2.0, 2.5, 3, 3.5, 4, 4.5, and 5. Okay, and your friend going to read the displacement and another friend recording. What happened is when the behavior of the material is a kind of linear, okay, or with small curve, this loading controlling test is fine. But when the structure have the behavior like the yielding like this, what happened is when you have 5.5, your friend can read this stand easily. But when it increased to 6, what happened is the material gonna deform a lot, and what happened is you're going to miss this behavior of the material. So what did you get? You only get that your structure gonna deform in the manner of the light blue, not of the green or the red. So some mistake occur here when you do the load controlling test. And in the lab, when you notice the big change, a large change of the deformation, you're going to switch from the load controlling test to the displacement controlling test. So in conclusion, load controlling test is good for the behavior of linear elastic region. So it's also good for the brittle material because the brittle material have the linear elastic to failure. Okay, but for the displacement controlling test, what we have is we divide the displacement into equal region. For example, the one who read the dialog, every 10 movement of the scale, they ask the loader to read the load. Okay, and then they increase it another 10, 20, read the load. 30, read the load. 40, 50, okay, 60, 70, 80, 90, 100, 110, 120, okay, and you may see, even though the material have this kind of yielding, the displacement controlling test will give you all the required data point along this, and you will get the exact curve as you like. So the displacement controlling test is the better one, and is appropriate for all regions of material behavior, no matter it is the elastic or it is the plastic, no matter it is the brittle material or it is the ductile material. The displacement controlling test always good. อาจารย์ why don't we need to study the load controlling test? We need to, because you're going to get the sense, the difference between this kind of testing, okay? And we have that. Then when the material fail, you got to take a note, sketch what the failure look like, okay? For sure, the cast iron will have the different failure compared to the steel. This is the failure of the cast iron. The failure of cast iron is going to have the 90 degree with the line of loading, okay? For the other, this is going to be for the steel because it has some necking, see, and this is going to be 45 degree. This is going to be 90 degree. This is caused the failure by the normal stress. This failure causing by the shear stress. And you got to notice also how the shear failure look like, okay? If the shape is very smooth, symmetric like this, this is kind of perfect. This is kind of a perfect test. But if there is something like this, there is some small mistake that occur during test, maybe due to the eccentric of loading, very small, due to the very small, let's see, very small, okay, eccentric of loading. So some part going to be get higher force and have some kind of different failure, some with the also part, okay? Okay, you got to take a look at appearance of the failure, also the cracking pattern, like symmetry, non-symmetry, and also the find and cause of the grain of the material. And what factors that is going to affect the tension test? I did a little bit mention about the eccentricity from the previous slides, okay? Let we take a look. If we have specimen, and if our specimen has the force that's applied passing to the centroid of the section, okay? By doing this, if you cut this specimen, what we have is the applied force going to produce the pure normal force, okay, equal to P. And this normal force, this internal normal force, will produce what? Will produce the average normal stress, sigma equal to P over A. However, when things change, when the specimen subjected to some kind of eccentric force, for example, if we have this and our specimen have the line of centroid here, and the force is applied here out of the line of axis with the eccentricity of E. What happens if you cut this specimen and then you draw the free body diagram of this one, what we have is they are going to have the internal force occur here. Okay, this is going to be the N. And since the P gonna rotate about this, and then the internal forces and moment on this section going to have M also. And if you may recall from the mechanics of material, okay, the N gonna produce the same normal stress. This is sigma equal to, actually N is equal to P, that's equal to P divided by A. Okay, the M, if you do the summation of the moment equal to 0 about this point, the P gonna time E gonna rotate like this, and the M gonna rotate in the opposite direction. So we have the M equal to PE, and we have the stress, okay, due to this moment in this way, this action. This is going to be in compression. This is going to be in tension. So you have tension here, and you're going to have compression here. And then the sigma here gonna determined by my over I when M is PE. And when you combine this, you're going to get what? You're going to get the new state of stress in which this is tension, this is tension. So this is going to have very large tension here. This is tension, this is compression. So this is going to be small tension. And then the stress due to this applied force going to be non-uniform. Unlike this one is uniform stress. This one is non-uniform, and you have sigma max here, which is going to equal to P over A plus this. It's going to P over A plus my over I, which is going to be higher than the sigma average, that is only P over A. So when you test this specimen gonna fail in this portion or in this portion earlier than the other portion. When it fell earlier, the strength or the stress that you get or the force that you measure gonna be lower than expect. So this P gonna be less than the real P. Okay, so coming to this, axial load that do not apply passing to the centroid cause non-uniformly distributed stress on the section, going to cause the stress distribution like I just mentioned before. This is going to be non-uniform. Okay, and one side will have stress higher than the average stress. That's I mean this side and this side. This side will fail early with the lower failure load. As I said, that's P is going to be lower than the axial load. And what happened is the axial load resistance capacity of the material going to be lower, and you should prevent this one and trying to check whether the force is applied passing to the centroid of the specimen every time you do the test. Okay, there's some ways to check that. And then another one is the test speed, which is not important because most of the time we do a slow test for each specimen, trying to study its behavior during the loading. Okay, and when the failure, the cast iron fail different from the steel, and during the steel test, when the behavior passing to the elastic to the yielding to the stand handling. At the stand handling, you will notice some kind what's so called the necking. Remember the necking, the necking, the necking. That means the cross section of the steel specimen will have smaller section when you increase the force. And then what happened is at the failure, the cross section of the steel gonna fail in this case, in this manner. What is this? The necking gonna produce the failure pane like this, and the angle here is about 45 degrees. And that means was this steel subjected to normal stress. However, when it fell by shear stress. Okay, the necking is the evidence that before the failure, the steel have some slipping of the plane of the steel gate. Okay, this slipping caused by the shear stress, and the failure plane is about 45 degrees with the longitudinal axis of the test specimen. However, for the cast iron has some carbon, okay, inside it, and the contact point between the carbon and the steel have some what's so called the micro crack. Okay, and the micro crack will open when it's subjected to tension. It's open. When it's open, the area that's used to resist the tension gets smaller and smaller, and then it will fail abruptly, and the plane of failure will look like the separation. This is separation of the grain. So this cast iron subjected to normal stress and fail by separation of the grain due to the normal stress. So this one will have the conclusion failure of the cast iron is due to separation of the plane, caused by tensile stress, okay, at the angle of 90 degrees with respect to the longitude axis of the test specimen. They are different. Ajahn, why they put the carbon into the cast iron? They put the carbon into the cast iron to improve the surface hardness, improve what's so called surface harden. Okay, why they need to input the surface harden? The application of cast iron is in the structure such as the railway. Okay, the railway support the train wheel. The train wheel produced by the cast iron. So in application, when the train break, the surface of the rail must be very strong. So they need to surface harden to get that strong surface to resistant to the friction due to the brake. Okay, so the rail will stop the train properly. And also, since the wheel when it's on the rail, okay, it's put the compression in the rail, and the cast iron has very high compressive strength. See, that's why cast iron is proper. We use this to produce the railway for the train or the railway for the crane. Okay, that is going to be the lesson of this. Okay, let's conclude. The steel, okay, have the necking before failure. That's necking due to the slipping of the plane of steel gate and causes by shear stress at 45 degrees. However, the failure of the cast iron is due to the separation of the plane of the steel grain due to the microcrack and the tensile stress, and it has 90 degrees with the longitudinal axis of the testing specimen. Okay, this is the end of the first part of the static tension. Let us go further for the structural member or machine that's going to be in compression. Let's take a look at the steel here. This steel is the column, so the force will apply from the top portion of the building, okay, transferring across the column, and the column gonna have to resist this compression, okay, by producing the normal stress, and then you can find the small stress here. If this is P, it's going to be P divided by the area of the column. Okay, you can compute the area of column easily. Next, taking a look at the machine here, that's we're going to move the earth to somewhere, and the earth going to have the weight of W, and you may see if you take a moment about the pin or hinge F, the W gonna rotate this way, and the hydraulic supposed to put the force to resist it and making the opposite clockwise rotation to the weight W. And if you draw the free body diagram of this hydraulic, okay, this one going to be in compression like this. We use a lot of machine in our construction sites, so it's better for you guys to trying to understand the behavior of that kind of machine, not only understand the behavior of the structure. Okay, so 5.2 static compression. We have the concrete for sure. That's usually used to support the compression, such as in the column. Okay, we also has the cast iron that's used to support the compression. What I've said is we have the wheel of the train that put the force onto the cast iron railway, right? And for the concrete, what we have is we put the concrete into the compression test, and then we draw the stress strain diagram of the concrete. Okay, and the stress strain diagram of concrete gonna be look like this. Okay, and this has the graph, and what we are interested in is mechanical property is sigma sub u. So in the concrete, we interested in ultimate compressive strength. This in steel design is have the symbol of F palm sub C, which is going to be the sigma sub u. Is going to be ultimate compressive stress of concrete. Okay, and then you also need to specify this when you buy the concrete, especially when you buy the ready mix concrete. You got to specify, I'm going to buy the concrete with the strength of 320 kilogram per square centimeter or 400 kilogram per square centimeter, and then you need to collect some concrete specimen in every 50 cubic meter, and then you test it and check it with what you really like, you really buy it. If you get the lower strength, you got to reject that, and it's going to have big problem, because most of the time when you test the concrete is 28 later than your build that concrete structural member already. So for the concrete, you need to be very careful on the testing of the concrete, and sometimes you also need to measure the modulus of elasticity of the concrete. which is going to be the slope. Okay, at the start of this is going to be the delta sigma divided delta strain. And for the cast iron, okay, for cast iron, you may have the cast iron both in tension and in compression. And you may notice that most of the cast iron has really high compressive strength compared to the tension. Okay, because the cast iron produced by putting the carbon into the steel to make the surface of the cast iron hardened to resist the force such as the friction during the train brake that won't harm the surface of the cast iron. Okay, and for the cast iron, you get this. You got to determine this is going to be the proportional stress, or most of the time it's going to be the same point as the sigma sub y, the yielding compressive stress. Okay, and most of the time you use the 0.2%, we set it equal 0.2% offset to determine it. Okay, for the stress strain in tension, you also use the same thing, and you get this one, and you may say the yielding stress in tension, that is going to be like 130, very small compared to 350. Okay, this is maybe just only 130, that is going to be 350. So most of the cast iron has high compressive strength. Okay, and that's mean for the cast iron, you got to determine the yielding stress, and also you got to determine the ultimate stress, the sigma sub f. Okay, here, or also the maximum stress that's occur here, that is going to be sigma sub u, and also the modulus of elasticity, that is the slope. Okay, most of the time the slope of the modulus of the cast iron is a little bit lower than the modulus of elasticity of the steel. Okay, what should we consider for the compression test? The same thing as the tension test. If this column subjected to this is going to produce, if you cut this and draw the free body diagram, it's going to produce what? It's going to produce the axial force, okay, applied to the axis that's passing to the centroid of the column. And if you take the moment here, you may see this one gonna rotate like this. So you got the moment here. And if you do the summation of f sub y equals to 0, n equal to p. And if you summation of the moment at this equal to 0, m summation of moment equal to 0, m equal to p times e. Okay, and what happened is the p gonna produce the compressive stress like this. Okay, and the moment going to produce the compressive stress, this one going to be in compression. Okay, and this one going to be in tension. And I should like it properly. This one going to be small. This one going to be in this one with intention, and this one going to be in this one in compression, this one in tension. So we got this. And when you combine them together, this is compression, this is compression, you get high stress here. This is tension, and this is compression, you got low stress here. So this is the point that the structure gonna fail early. So coming to this, the factor that affect the specimen in compression, the first one is eccentricity. Okay, the axial load that do not apply passing to the centroid cause the non-uniformly distributed stress. What causes here? This is non-uniformly distributed stress. One side will have stress larger than the average stress. This is the point that has some large stress. This side will fail early with the lower failure load than the actual load resistant capacity of the material. So if you put the force eccentricity, you will get the lower failure load. Okay, and that's going to make you in problem in some trouble in some situation. You got to very careful when you apply the force to this compression specimen. Okay, and the second one is the buckling. You may put the ruler and then you push it. Okay, you may see that that's going to have the lateral deformation. That's called the buckling of the specimen. We don't like to have this because buckling is not a material failure. Buckling occurs in the long column. Okay, buckling is kind of what's so called the stability failure. It's not a material failure, so we need to prevent it. It's only occur in slender column. That means since it's occur in slender column, our specimen supposed to be very short and fat, something like that. Supposed to be like the concrete specimen. The concrete specimen have the diameter of 150 millimeter and the height is about 300 millimeter. So it's going to be very choppy. Okay, not cylinder. The compressive specimen in this case must be short with large cross section like this one. And what happened is the testing machine must have high loading capacity, and the measurement of the deformation and the force must be with high accuracy. So testing material in compression may be expensive. Okay, and the third is usually occur in the concrete. Many times when we test the concrete, the Thai industrial standard and the Astm, for example, they will ask us to cap the specimen both end with sulfur. Okay, in my generation we use our sulfur to cap it because we kind of trying to reduce the friction between the specimen and the loading head. The friction force, okay, prevent the lateral deflection of the specimen. The specimen, when it's subjected to the compression, will buck out like this. And what happened is on this portion they have friction. They prevent the movement of this end. Okay, and it's going to produce the stress, and this stress combined with the compressive stress is going to build the combined stress. It's going to do the larger than usual stress, and then the material will get the strength or the loading lower than the actual resisting capacity of the material. Okay, so we need to cap the specimen with very slippery material. The sulfur usually used in the past, but this time the sulfur didn't use much. Most of the time we start to use plaster. Anyway, when you do the testing of the specimen, you cast the sulfur into the cap. You must be very careful. Okay, because sulfur really harm to our health. But anyway, for the plaster, you got to have skill, really high skill to do so also. Okay, talking back to the specimen, we consider the metal first. According to the Astm E8, okay, the specimen should not be too short. If it's too short, it's going to have the effect of friction, and should not be too long. If it's too long, it's going to have the buckling problem. Okay, too short, you're going to have friction problem. So the specimen for the metal in compression should have the ratio of H over D in between about like 2 D to 10D usually for the friction and the buckling. Okay, and then this is the conclusion of this 8 to 10D. That we prevent buckling to reduce the friction. Okay, it should not shorter than 2D. Okay, and for the concrete, the Astm C31, you know the Astm, right? American Society. A is American Society for Testing and Material. That's for concrete, number 31. Okay, that is going to be in accordance with Thai Industrial Standard 409. The diameter of the concrete cylinder, okay, should not larger than the aggregate at least 3 times. Okay, aggregates for ash, such as crushed stone. Okay, crushed stone is bigger than the sand, so mostly we use the crushed stone as the reference of this crushed stone. Okay, so the size of the crushed stone that we use is about 1 inch to 2 inch, or 25 millimeter to 51 millimeter. So that's why the code specify this one for 150 millimeter or 6 inch. And due to friction, Astm said this one supposed to be 2D. That is going to be 300 millimeter. So we have this kind of specimen, and all the standard said you got to cap the end of the specimen before testing. Okay, the testing machine that we have 3 types of laboratory for compression. One is the lab number 5. It's a compression of the wood parallel and perpendicular to the grain. Okay, so the wood have some grain. So most of the wood can carry a large force when it's subjected to the force parallel to the grain like this, and it's going to carry less force when the force applied to the wood in parallel to the grain. Perpendicular to the grain like this. Okay, and also we do the compression test and fractional test of brick. Okay, we use brick a lot in our building, and we also do the compression test of the concrete. Okay, this is going to be the 2000 kilonewton compression machine. For the fracture of the brick, we will test in this machine here. And when we observe the behavior of some material are different in compression and tension, such as concrete and cast iron. Most of the brittle material have different tension and compression behavior, but for the metal such as aluminum and steel, it has the same kind of behavior. And what we have is cast iron has similar linear elastic region both in compression and tension. What we have is the first portion of the cast iron. That's this portion, and this portion has very similar, both the E, which is the stiffness, okay, very similar. However, it's different in sigma sub y, because sigma sub y, this one about here, about 130 we have before, and this one for 0.2, you may get this one higher. Okay. And cast iron fail abruptly when reach its tension strength. Due to what? Due to the cast iron has the carbon inside it. When the contact point between carbon and the steel have some micro crack, when you put them in tension, the micro crack will open very fast, and then the area that's used to resist the tension going to be reduced, and it fail abruptly. However, when it's in compression, okay, the compression will cross the micro crack. The micro crack will cross the micro crack, push the micro crack to each other. Okay, and with the lateral expansion due to the boson effect. I mean this, when you patch this one, okay, this one have the boson effect, have lateral, so the area increase, okay, and it take a lot of forces in compression. And when you notice the failure of the metal, you may see that this is for the untested specimen, and when you put the compression for the gray cast iron, it has 45-degree crack, okay, which is due to the shear stress. It also occur in the aluminum alloy. However, for the hot cold steel, it has large deformation. Okay, they are different, and you may have gray cast iron and aluminum fail with diagonal crack. Okay, 45-degree, and aluminum has larger contraction before failure. Okay, that means it can contact or deform more due to its more ductility before failure, and it's going to crack at 45-degree. For the hot rolled steel, it fails by large deformation, like I said before, shaped like a barrel, And for the concrete, sorry, this is in Thai, sorry, this for the concrete. It fails with diagonal crack similar to gray cast iron and aluminum. However, the crack is kind of have larger angle due to what? Due to the inhomogeneous of this concrete. It have the sand, it have the cut stone, it have the cement paste, okay, and it also have the friction that increase the crack to be the 50 or 60-degree with vertical line, different from the metal that have very fine smooth material. For the failure of the brittle metal in compression, okay, one is for the shear cone. The shear cone occur in the specimen, in the concrete or the mortar, okay, the stone cube, that's a cubic, okay, cubic is have the picture of the cubic. Unlike most of the cylinder, this is called cylinder. This is called cube. Okay, cube is based on British standard. Okay, most of the cylinder based on the US standard or Astm. And the cube, if you put it into concrete, is also important because most of the pavement, okay, what pavement? Road pavement is going to subject that to the force of the wheel This is the wheel force. Most of the wheel force apply like this. So when you test in the cube, okay, it's going to similar to that. So most of the department of highway, DOH, okay, they may use the cube for the concrete. But in the construction of the building, most of the time we use the cylinder, okay, for the building, okay. But for the pavement, sorry, pavement, okay, we may use the cylinder. Cylinder have the hourglass. It have the shape like the shear cone, like this. For the concrete and the cast iron, they have the mix, okay, of this crack, usually failure in cylinder of this. And this is for the concrete. It have the tensile splitting on the top and shear cone at the bottom. Okay. Why the shear plane of the cast iron is about 45 degrees? Okay, this can be proved by using the Mohr circle. But the shear plane of cylindrical concrete is about 50 to 60 degrees. Yeah, because of what? Okay, because the concrete is non-homogeneous material. It has the sand, cut stone, and cement paste. So the stress at a point is will different to each other. Okay, so the causing both the compressive stress and the shear stress, that's due to different in material, and the failure will due to the combination of this stress. Not only the compressive stress, it have the shear stress also, and the friction at the head of the specimen also one main thing that's caused the failure of this kind of cylinder concrete. For the wood or the timber have different kind of failure. It's different from the concrete and the cast iron. Since timber have grain, okay, the grain parallel to the length, okay, the failure of the timber are quite different, because timber is the natural material. The grain can be in many directions. But anyway, the failure of the timber can be classified as crushing. Okay, splitting. And splitting is mostly in the wood that's subjected to the force parallel to the grain. Okay, and shearing. Okay, we classify like this. The timber subject to compression parallel to its grain. Usually fail by clutching. The first one, that's parallel to grain by clutching. And timber subjected to compression parallel to its grain usually fail by buckling of timber grain, causing the rupture like this of the timber. Okay, that is the end of first part of chapter 5, characteristic of tests. I hope you may catch up some important point, such as why we test steel in tension, why we test concrete in compression. During testing the steel in tension and compression, what should be aware of, such as the eccentricity of the loading. We are supposed to put the applied force passing to the centroid of the section. If not, the eccentricity will produce extra stress, and the result going to be lower than the actual one. And we also like you to understand how the type of specimen are set, such as the steel. Some steel you have to reduce section. For the concrete, the specimen cannot be too tall because it may cause some kind of buckling. Okay, that is kind of the end of the first part of chapter 5, and the discussion of the materials are important to our civil engineering application, because it includes the steel, it includes the concrete, it includes the cast iron, and also the aluminum. Okay, so I should end this clip here, and I will have the second clips follow this.